Welcome back. Today's review exercises for Chapter 23 will help us get a grip on determining the accuracy of averages and the process for doing so. A box of tickets has an average of 100 and a standard deviation of 20. 400 draws will be made at random with replacement from this box. Estimate the chance that the average of the draws will be in the range 80 to 120. This is, I can already see the chance here. Does anyone already know the estimate of this chance? Well, let's walk through it. So, the sum of the draws So we're going to get the expected value of the sum and then get our expected value average. Damn it. Sorry. Shh. Starting to get chaotic here. One moment. No, back up. No. Back up. There's mosquitoes coming in. Get out. Yep, sorry. Okay. We'll get the expected value of the sum. We'll get I know, I don't stop it for those brief points because then it makes just a pain later. So expected value for the sum. Oh wait, the chat is in the wrong place. Sorry about that. Okay. And we'll get the expected value for the average. Then of course so let's see here, the expected value of our sum is, we have an average of 400, so we know the mean of the box is 100. We know already the standard deviation of the box is 20. Excellent. So we can get the expected value for the sum as the mean of the box times the number of draws. The mean of the box is 100. The number of draws is 400. So the expected value is 40,000, give or take. Standard error. Let's get our standard error. Oops. The square root of the number of draws times the standard deviation. The number of draws is 400. Our standard deviation is 20. So we end up with a standard error for the sum here of 400. We already know the expected value of the average is going to be 100 because that's the average of the box. And we need to get the SE of the average. Damn it. So the SE of the average is just the SE for the sum out of the number of draws. It's simple enough. 400 out of 400 is 1. So the standard error average is 1. So if the average, the expected average is 100, what's the chance that the average of the draws will be within 80 to 120? Well, if the standard error is 1, the chance is going to be almost 100%. Remember, it's not 100% because we can't ever say 100%. We can only get to infinitesimally close to 100%. But this is very close. Then what's the chance that the average of the draws will be in the range of 99 to 101? This one is very easy to see. What's the chance that this estimate is within plus or minus 1 standard error? Yep, we're looking for a percentage, a percent chance here that the average of the draws is in the range of 99 to 101. We don't need to do any math to do this one, really. We can just visualize it because we know that our average is 100 and that's 0 in standard units. And over here we have 1 standard error, -1 standard error. Oops. And the values that correspond to these points, since the SE is equal to 1, the SE for the average, then these are 101 and 99. So what's the percentage here that falls in this region? It is the z-scale. This is always, the standard scale is always the z-scale. It's the standard scale. Standard units. Sorry. There's a mosquito in here that's been going after me for a while, and I had a chance to maybe get it. I'm not sure if I did. Yeah, it's 68%. Exactly. Thank you. Woohoo! 68% here. It's always 68% estimated within plus or minus 1 standard error. So there's a 68% chance that the average of the draws will be within 1 plus or minus 1 standard error, or 99 to 101. Very good. Now let's look at item 3. A real estate office wants to make a survey in a certain town which has 50,000 households. to determine how far the head of household has to commute to work. A simple random sample of 1,000 households is chosen, and the occupants are interviewed, and it is found that on average, the heads of the sample households commuted 87.7 miles to work. The standard deviation of the distances was 9 miles. Okay, and we can get the average. Here are the average commute distance of all 50,000 heads of households in the town. It's going to be estimated as, we already know the term that it's going to go here is going to be our expected value average, right? And this estimate is likely to be off by a standard error for the average, by a standard error or so. We have lots of the information we need already. We know that on average, we know that the N is 1,000. The average for the sample is 8.7 miles. The standard deviation was 9. And yes, we will get the expected value for the sums on the way there, but, oh wait. So let's move into our analysis here. First step, well, we know the mean of the sample is 8.7. So what's the expected value of the average? It's 8.7. We have the mean of the sample. We already know it. Since we know the mean of the sample, and we're getting the average commute distance, we're bootstrapping to get to this average. So we already know this is going to be 8.7 miles. The real issue is to get our standard error. Remember, this is a box with 50,000 tickets. And each ticket, in this case, shows the commute distance. This is not a simple box. That's why they gave us the standard deviation instead of using our shortcut. And the data are just like 1,000 draws from the box. So we don't know the standard deviation of the box. We just know the standard deviation of the sample distances, but we can estimate it by the standard deviation of the data as 9 miles. And the standard error for the sum is, of course, the square root of our number of draws, or N for the sample, times the standard deviation, 1,000, times square root of 1,000 times our standard deviation of 9. So this is approximately 285 miles. Okay. And then we can simply get our standard error for the average by taking our standard error for the sum out of the n. So it's 285 out of our n of 1,000. So the average, the standard error of the average is 0.3 miles. So this estimate is likely to be off by 0.3 miles or so. If possible, find a 95% confidence interval for the average commute distances of all heads of households in the town. If it's not possible, explain why not. Well, what do we think? Is it going to be possible? Yes, it's generally possible, as long as we would expect this to be normally distributed. And we haven't been given any reason to think it's not at this point. It is a simple random sample. If this wasn't a simple random sample, then no, we couldn't. But we do have a simple random sample here. We'll get our confidence interval, which is, remember, 95%. So this one will be 2 times our standard error plus or minus the average. So in this case, it's 2 times our standard error of 0.3 plus or minus our estimated 8.7 miles. So this interval is 0.6 plus or minus 8.7. We normally see it written as 8.7 miles plus or minus 0.6 miles, or give or take give or take 0.6 miles. I could also ask a question that said, we can be 95% confident that the average commute distances of all heads of households in the town is between blank, is between one blank and another. Those blanks corresponding to 8.7 minus 6, so 8.1, and through 8.7 plus 0.6, or 9.3. Does everybody see how you could report a confidence interval like that in different ways, but one of which might be to say we're 95% confident that the range will be between these two scores. Okay. I don't think we need to do that. Do you want to find another confidence interval? Let's skip it. Yeah, I think we've done enough confidence intervals, but we'll do 5, which is finding another confidence interval. In 721 of the sample households, the head of the household commuted by car. Find a confidence interval for the percentage of households in the town where the head of household commutes by car. Okay, well, this is pretty easy. We have a box with Now we've got a 0, 1 box here where there's 0 is no car, and the 1 is did go by car. And we know the proportion in here too in our sample. The sample proportion had 721. This is 80,000 for each household in town. Yes, information. So no car is going to be 50,000 minus the, oh wait, in our sample, excuse me. The box has 50,000 tickets. Our sample has, how many? 1,000. So our 721 are going by car, 279 reported no car. So we know the expected you should already be feeling pretty, we already have the process down here for thinking through our terms and a process to getting our confidence interval, right? We're going to need to get the expected value for the sum. We'll need the SE for the sum. We'll get the expected value for the average, the SE for the average, and we'll use this information to get our confidence interval. We'll also get the mean of the box. And the standard deviation of the box. We already know that the mean of the box is going to be 0.721. Because that's the, we're estimating from the fractional representation in our sample. And we can get the SD of the box by using our shortcut, big minus small, times the square root of the big fraction times the small fraction, or 1 minus 0, times the square root of 0.721 times 0.279. And the SD of the box then is approximately 0.45. Next, we can get the SE for the sum, the SE for the number of ones in the box. The square root of the n of our draws times our standard deviation. So it'll be the square root of 1,000 times the standard deviation of 0.45 to give us a standard error sum of about 14. And then we can easily get the standard error for the percentage by taking our standard error for the sum, dividing by our n, or 14 over 1,000. So the standard error average is 1.4%. And we would expect that the, we already know this is 7. We don't actually need to go through this one because we know the expected value of the average is going to be this percentage, 72.1. It's just a percentage representation of our box proportions. We've inferred the box proportions based on the proportions in the sample, e.g. we bootstrapped, and we can just convert our proportions to percentages. So we now know that we now have all the information we need to get our confidence interval for the percentage of households. Our confidence interval is just equal to our 2, a 95% confidence interval, so it's 2 times our standard error plus or minus the average. The expected value average. All right, so we can see here this will be 2.8. Thus, the percentage of all households where the head of household commutes by car is 72.1%, give or take 2.8%. And it is helpful to write this out in words. You might think, gosh, but aren't these sentences repetitive? Well, sure, lots of things we do in statistics are repetitive. The point is to repeat things at the right time and place, but especially doing the sentences will help to get you prepared for our next unit where we're writing more sentences because we're writing up some results. So this is getting us ready for the next step. In addition to being conceptually helpful. Well, good. A city government did a survey of working women to see how they felt about juggling jobs and family responsibilities. Businesses, unions, and community service organizations helped distribute the survey questionnaire to local or locations where the women could pick up copies. 1,678 out of 2,800 respondents, or 59.9%, checked the item "stress is a serious problem" on the questionnaire. From these options, let's select one. Which is correct? Well, to approach this problem, you have to start always with any of these problems. Start at the first. Your first question should be, is this a simple random sample? Is this a simple random sample? What do you think? No, it's not. So now that we have established that it's not a simple random sample, what do you think of these options? Which one is correct? Well, neither of them is correct, so it's 3. Yes, very good. Neither's correct. This is 3 because this is a convenient sample, so neither of these would be correct. Very good. Boy, I think we should just skip. This is just another, we'll just do another confidence interval. You should definitely want to practice it. Obviously, you want to feel comfortable with all these calculations for the exam, but we have done lots of confidence intervals here. We can do one more quickly if you'd like. Let's see. It'll be our last confidence interval. Okay, let's skip it and go to 11. The figure below is a probability histogram for the average of 25 draws made at random with replacement from the box 1, 2, 3, 4, 5. Or is it? Is something wrong? Well, how would we know if something was wrong? First thing we could do is we should think about what is the standard error and average of this box? Well, what's the average of a 1, 2, 3, 4, 5 box? 3, probably is actually 3. I don't know. But we can find the average quickly enough. Yes, it is 3, correct? So we know our mean is 3, and I'll skip through some of these calculations to the observation that our standard error for the average here would be about 0.3. So given that our standard error is 0.3, does this seem like a reasonable probability histogram for this box? Nope, It's not. It does look like a probability histogram. It's that's the trick. I mean, sure, it looks, but it's not the probability histogram for this box because there's way too much spread in these data. If the standard error average is 0.3, then one standard, let's imagine our standard units here. Well, we would have to have one standard unit, gosh, be like right here. And we would easily make it then 0.3 to a second standard unit. 3.3, we're at 3.3, right? 3.6, we get up to 3.9. That's a third standard unit. Wow, there's way too many standard units. We have 3 standard units, 6 standard units, well before we even make it to the edges of the distribution. So it's not a reasonable probability histogram. Something is wrong. There's just way too much area outside of the range, the expected value plus or minus 3 standard errors, which you should use when you're judging something like this. You want to use the rubric of the expected value plus or minus 3 standard errors, because remember, that's the expected spread. Essentially. Okay, well, excellent job on these items. As you can see, the formulas in this chapter were just a small extension of our earlier formulas, and a small but important extension as we will use these new values and these new statistics pretty extensively in our next unit on tests of significance. Remember, for the most efficient way, do some statistics every day.